Okay, so let's get started in chapter 30, talking about induction and inductance. Right, and so the general idea here is that we saw if you have current in a wire that generates a magnetic field. So we can say moving charge generates B field. Right, which should kind of make some sense because a charge had to be moving to experience a force from a magnetic field, and now we kind of have the reasoning behind that is that moving charge creates magnetic fields. And once you have two fields interacting, you can get forces and potential energies and all sorts of stuff. And so current is moving charge. And so currents generate magnetic fields. Okay. And so then the other thing we're going to kind of get into is if a current can make a magnetic field, then a magnetic field can make a current, right? So we talked, if you have a wire in a magnetic field and you move it, you can generate a current. But what we can also put is the changing magnetic fields can create currents. And so that's going to be the main idea for what we talk about today. And so we start by discussing two experiments that were conducted by Faraday back in the day. And so the first one, let's say you start with an ammeter, and we can do these in class, right? And so if your ammeter goes up and connects to a loop of wire, right? And if you wanted to make this more drastic, you could have it be a coil of wire, which is probably what we would end up doing in class. And so if you take a magnet, right, magnetic field's coming out of the north end, and well, let's say you start relatively far away with it, and you take it and you push it really fast towards that loop. So what happens is this loop of wire went from having no magnetic flux to having some magnetic flux. And so what we'll see is, well, first let's define magnetic flux. So we had electrical flux, which was the integral of E dot dA, right, and that came up in Gauss's law. And so for a magnetic flux, that's just going to be the integral of B dot dA. Right, because it still is just magnetic or field lines through an area is the flux, right? So we can define that. And so what Faraday's law tells us you can generate an EMF equal to negative d phi dt, right? Where we have capital phi being our flux. And so the change in flux generates a potential, an EMF, a voltage, however you want to say it. And then we can have Ohm's law. And we can get a current, right? And so this is the first of Faraday's experiments where he actually had a magnet. The second one is a lot more complicated to draw, but not terribly more difficult to understand. And so we have this come out. We have a loop of wire, comes back in. And then what we have is, I'm going to draw this in a slightly different color. We have another loop of wire, terrible, nearby. What is it? Is going to go to some kind of a power supply, and then a switch. I guess there's also a resistor in there because you need to have something to dissipate energy. Right, so we have a switch, a resistor, power supply. And so we had discussed the magnetic field traveling in a loop, whether we had it be, just a loop of wire with some current. Right, this would get us a magnetic field going up. Right, by the right-hand rule. We curl our fingers around counterclockwise, our thumb points up. And so if we have this set up such that we're going to have some current flowing this way, and then I guess it would go kind of around here. So we could get that we get a magnetic field that kind of points this way. Right, that only will pop into existence once we close this switch. And so the idea being, once we close the switch, the current flows through, we generate this magnetic field. All right, this magnetic field is going to change the flux through this loop, which is then going to generate a current. All right, so just like here, us moving this magnet back and forth would generate a current that we could measure on an ammeter. Here, by flipping a switch up and down, we can also generate a current in a separate loop of wire. And the whole idea there is that we are changing the magnetic flux through that loop, and so we generate a potential that goes around that loop. Okay. All right, and so we had said, what did we say? Phi sub b is the integral of b dot dA. And so if we have a uniform B through a perpendicular area vector, well, through a perpendicular surface, I guess we would have to have parallel vectors through a parallel area vector. Right, so that would look something like, if you have an area and we have maybe our magnetic fields going into the board. And hell, if it's uniform, it can be, outside as well. All we're concerned about is what goes through that loop. I guess I didn't do a good job at drawing a uniform field. All right, that's about the same spacing as everything else. Then we can say the flux is just equal to BA. Okay. Right, so if the magnetic field's perpendicular to the surface, right, so parallel to the area vector, then we can just multiply them together. And so let's see. We know magnetic field has units of Tesla. Area has units of meters squared. And so we can say phi sub b has units of 1 Weber, which capital W lowercase b, is equal to 1 Tesla per meter squared. Okay. And so then we had said Faraday's law. That's one we're going to want to hang on to. It's going to come up to be important. And And so this is what we had to be true for one loop of wire. If we imagine that this was a coil, I guess we'll do a slightly different color. And so now maybe there's two loops of wire. Imagine they line up perfectly. We would imagine that we have twice the flux. And so what we can do is we can say the EMF we generate is equal to N, negative, we'll get into the negative sign in a bit, times d phi dt. Right, and so that, if we have the same flux, change in flux going through one loop, if we have multiple coils, we just multiply by however many coils there are. Okay. And so we can conclude more loops, greater EMF. Okay. And so now we're going to get into Lenz's law. Nope. 3-4. And so essentially what Lenz's law tells us is an induced current has a direction such that the magnetic field due to the current opposes the change in the magnetic flux that induces the current. Right, that's a mouthful right there. Right, how many times we use the word current? 1, 2. Well, only 3. That's not too bad. Felt like I said that a lot more times. Okay, so what does that mean? Let's say we have our loop of wire, right? We'll just say one loop for now. And we want to take a magnet, north pole, and I guess, just we do have the south, but we're really only looking at north. And we take this and we cram it through this loop of wire. Right, that's clearly going to change the flux experienced by the wire and generate a magnetic field. And what we get is that the generated magnetic field is going to try to oppose the change in flux, right? And so we have an increasing flux going down through the loop, and so we are going to create a magnetic field that will oppose that, right? And so we would say that this would make a, if you're looking from the top down, counterclockwise current, right? And then if we right-hand rule that, that makes a magnetic field that points upwards, and that would oppose the increasing downwards flux that we experience. And we'll do a lot of practice problems with this. And so, if we look at this, if, let's say, this uniform magnetic field was decreasing, right? And so as B decreases, we're getting a decreasing amount of flux going into the page. And so we are going to want to create a magnetic field going into the page. And to do that, right, if we right-hand rule it, we would need a clockwise current, right? Because if you curl your fingers around that way, your thumb points into the board. And so if this external magnetic field were decreasing, right, if B was getting smaller, we can see the flux would be getting smaller. And so we are going to create an EMF that's going to create a current that's going to create a magnetic field to oppose this, is what Lenz's law says. And we will do tons of practice with that in class. Let's see. That's pretty much all we have for today. So I'm just going to do some conceptual examples. Let's say we have a magnetic field coming out of the board. And we have, let's say, a square loop of wire. And let's say we're going to drop this loop of wire, so it's going to fall and start to leave this uniform magnetic field. You know, say the magnetic field's confined to this space. And so are we going to make a clockwise or counterclockwise current? Okay. And so let's think here. So initially, well, probably shouldn't erase that whole thing. Let's say it has some area A, magnetic field has some strength B. So initially we have some phi sub B is equal to BA. So if we come back at some point later, and maybe now we only have this much of the loop in the magnetic field, we see that we are going to have a much smaller flux, right? So this is going to decrease. And so what we're going to want to do is create a current that is going to create a magnetic field coming out of the loop because we lost a bunch of flux coming out of the board, right? And so if we want to make a magnetic field coming out of the board, we would have a current that's going counterclockwise. Cool. And so let's do that, but backwards. Let's reverse that whole problem. And so now let's say we start with the loop outside of the field, and we're going to push it into the field. Well, so initially, we have no flux. Or if you want, we could have a little flux as a treat. Excuse me. Yeah, thank you. And so let's say we have a little bit of flux at first, and then we're going to push this into our external field, and now the whole thing is full of flux. Well, now we're getting an increasing flux coming out of the board, and so what we want to do is make a magnetic field to oppose that. And so we're going to try to create a magnetic field going into the board to try to maintain the flux we initially had, which was 0 or small or whatever. And so if we want to go into the board, the current's going to have to go clockwise, and we would get a clockwise current. So those are just a couple examples. We will spend more time on this in class. All right.